Okay, so today we're going to be talking about Leetcode number 623, or add one row to a tree. So first thought, whenever you talk about binary search trees or binary trees, DFS and BFS should be the first things on your mind, because there's a 90% chance that that is what you're going to use when it comes to binary tree problems. So given the root of a binary tree and two integers val and depth, add a row of nodes with value val at the given depth. Note that the root node is at depth 1. Okay, so in this example on the right, the root node would be at depth 1, and then every level below it, you increment by 1. So this is depth 2, depth 2, depth 3, just like that. This whole thing is depth 3, this whole thing is depth 2, and this whole thing is depth 1. Given the integer depth for each not null tree node cur at the depth minus 1, create two tree nodes with the value val as cur's left subtree root and right subtree root. Cur's original left subtree should be the left subtree of the new left subtree root. Cur's original right subtree should be the right subtree of the new right subtree root. So this might get your tongue twisted for some reason, but it does sound a little confusing when you first think about it, but it's actually pretty straightforward when you do look at the example. So they're going to basically give you two numbers. They're going to give you a depth. In this case, it's going to be 2, and they're going to give you a value 1. So this value is the value of the tree node which you need to insert. So you're going to make two tree nodes, or 4 or 6 or 5, depending on how many you can make in that depth, and put this value in as that tree node. And then this depth is the depth you're going to insert the node at. So remember when we talked about the depths right here, right? So 1, 2, and 3. So since in this case, since the depth is 2, at depth 2, you're going to add two tree nodes with the value 1. So then it goes root, two tree nodes, and then the root's original left subtree will be the left subtree of the left value tree node. See, it's a little bit confusing, a little tongue twister. And then the same thing for the right subtree. The right subtree will be the right subtree of the right new tree node, which is basically what these 3 points are talking about. And the last one is basically like an edge case we have. If depth equals 1, that means there is no depth, which means you insert it at the root. Since depth equals 1, you will insert the new tree node at the root. Then create a tree node with value val as the new root of the whole original tree, and the original tree is the new root's left subtree. So basically what they're saying is if the depth is 1, so instead of 2, the depth is 1, you will put it at the root, and this whole subtree in general will be the left subtree of the root. So in this case, it would be 4, then 2, then 6, then vice versa, 3, 1, and 5, right? So we're going to be making an edge case. Make sure you keep that in mind. We're going to be making an edge case to that if the depth is 1, then this whole tree will be the left subtree of our new tree node. So like what I said earlier, this is either a depth first search or a breadth first search approach. Those are the easiest ways to go about this problem, or most binary search problems. In this case, I'm going to use the straightforward breadth first search way using a queue. So basically, I'm going to go through the code and I'm going to do some drawings on the right side to make it easier to understand. So we're going to first declare a variable tree node parent, which we'll be using in this while loop, which I'll get to later. And then we're going to declare a variable to keep track of our current depth, right? And so since our current depth always starts at 1, we're going to put 1. And then we're going to create a size, which we'll also use later in our breadth first search approach. So this is the edge case we were talking about. If depth equals 1, we're going to return a new tree node, val root null. So basically this val right here, we're using this constructor right here. We're going to use this val as the current value of our tree node, right? So this dot val equals val. The root, remember, is going to be the left subtree. So the left subtree of this current tree node we're in is going to be the root. So then it's going to connect everything that's below that root to the left subtree of the tree node that we're creating right now. And then null, because we don't do anything with the right subtree. As it's said in the bullet point, if the root is where you want to put the tree node, the left subtree of that root is going to be the original subtree, which is what this code is doing right here. So as a typical approach to BFS, we're going to use a queue to keep track of which level or depth we're on in the binary search tree. So the first thing we're going to do is add the roots. So the first tree node in this case will be 4. So we're here right now. Okay, so our queue currently only has 4 in it. So we're going to make a while loop while queue is not empty. So this will only end once queue is completely empty. And in this case, as you can see, there's a 4 in it. So it is not empty since we already added the root before the while loop. And now we're going to take the size of the queue. In this case, it's going to be 1. So we could traverse through the queue and pop each time, right? Since we're going from level to level to level, we're going to create the queue as in each level has all the nodes in that queue. I know it might sound confusing, but in this case right now, in level 1, what are all the nodes in level 1? 4. So 4 is in the queue right here. And once you reach level 2, the queue will be filled up with 2 and 6. And once we reach level 3, the queue will be reached with 3, 1, and 5. So this is just, if you've never done a BFS approach, this is the typical way of doing it, and it's really easy once you understand the basic parts of it, is that we're going to use a queue to go through each level. So once we have the size, we're going to traverse through it until we get to the size, right? So in this case, it's the size of the queue is 1. So once we're in this for loop, we're going to initialize parent to the first thing in the queue, and we're going to pop it or pull it in Java's case. We're going to pull the queue. So in this case, the parent will now equal 4, and this is now queue. Queue is now empty because we pulled it. And remember, when we pull in Java, it actually returns the thing that we pulled or we deleted. So the parent will now equal 4. So that's the value of the tree node. Okay, so I made some more variables so we could keep track of it easily. This is the depth, which was passed into the function. This was the value that was passed into the function. And this is our current depth variable that we're in. Sorry if it's a little bit messy because I'm using a mouse pad, so it's kind of hard to use. But our current depth is 1, and the depth we want is 2. So this if statement right here checks if depth equals current depth plus 1. All right, so we're going to take current depth plus 1, which equals 2, right? And that does equal the depth up here, the one that they passed into the function, right? And you'll see the whole point of this once we go through the first if statement. So these two statements right here is what we'll do once we know that we're at the depth above the depth we're supposed to be, right? So in this case, the if statement checks that this is 1, this is 2. We want to insert it to. We're currently at 1. So the depth that we're going to insert in is below us. It's going to be below us, right? Because we're going to need to somehow reference this parent node to 2 children nodes, right? So we're going to have to go to the depth before it because we won't be able to do it if we're currently at this depth, right? We're going to need to do it at the depth where the parent node is. So as I said, these tree nodes right here create the 2 nodes that we want. So it creates the left node and it creates the right node. So we create it with using val and then parent.left. Parent.left is basically making sure the subtrees still come align with each other even after we insert the nodes. So parent.left is this right here because this is parent, right? As we said right here, parent is value 4, tree node value 4. And then the right parent is this right here. So this left tree node will have the children of parent.left, and this right tree node will have the children of parent.right. This left tree node will have the children of parent.left, and this right tree node will have the children of parent.right. And right here, we just make sure that we actually change the children of the parent itself that we're on right now, right? So parent right now is 4, and we need to make sure that the children are actually the values which we just created, left and right. So parent.right and parent.left. And now we have our whole entire tree fixed, and we inserted our 2 nodes that we wanted to insert. Okay, so now I'm going to quickly go through my own example to make sure that we actually grasp the BFS way, how we actually go through BFS. Since this previous example only went through it once, let's go through it again. So in this example, the depth will be 3, right? And the value will be the same. It'll be 1. The value doesn't really matter. The value only really matters right here when we actually make the tree node. So the depth will be 3 right here, this level right here, which means 2 will have to point to 1 right here and right here, and 6 will also have to point to 2 more ones. And then we're going to have to create the left subtree and the right subtree of the ones accordingly. So basically, once we do this, it should come out to this. I know it's a little like scuffed, but these nodes won't be there anymore. It'll just be a normal 4 to 2, then 4 to 6, right? And then these children nodes are now going to be 1. And then the left subtree of this 2 will be the left subtree of the left node. The right subtree will be the right subtree of the right node. So this one right here. And then the same thing for the 6. The left subtree will be the left subtree of the original node, parent node, and the right subtree will be the right subtree of the original parent node, which is null. So again, we add the root, right? So our root is now at 4. And we go through the queue and we check the depth, right? The parent will now be 4. We delete from the queue, and is depth equal to current depth plus 1? So currently we're at depth 1. We need to get to current 2 because 2 plus 1 is 3, and which we're not at. So we're not there yet. So we skip this if statement. And now we add parent.left and parent.right if they're not null. We make sure we add the children of the current nodes that we're at. So now the queue is not empty now because we now have 2 and we now have 6, right? Since we added the parent.left and we added the parent.right. So now we pass this part right here, and now we increment our current depth because we're now at the second level. So now current depth does not equal 1, it equals 2. So now we do the same exact thing. Our queue is now size 2. We're now at current depth 2, and now our parent equals 2, right? Because after we do this, we delete the first thing in the queue and we assign it to parent. So now depth does equal current depth plus 1. As you can see, current depth is 2, and the depth you want to get to is 3. So 2 plus 1 equals 3. So now we're at the parent node of what we should be at. So now, as we said, we're going to create 2 nodes, and we're going to assign the left subtree and the right subtree to these nodes, and the parent.right will equal the new tree node we made, and the parent.left will equal the other tree node. So now, after we did this piece of code, we now have this right here. So now this whole left subtree, including the root, is now correct, right? Because we got to our number 2, and we assigned the left and right children, and we made sure the subtrees align also. And then once we reach here, we're going to add to our queue 3 and 1 because we added parent.left and we added parent.right. And then we're still in this for loop, so we're not at current depth yet, since the size equals 2 and we're at 0. So now we're at 1, right? So 1 is less than 2, and once we do I++, yes. So parent equals q.poll. So now we take out the 6, our parent doesn't equal 2 anymore, and we add the 6 here. So it's important because it makes this queue breadth first search process makes sure that each node on the level will have the right children node. So now that our parent is 6, we do the same thing here again, and we add this 1 as its left child, right child will also be 1, and then the left subtree will be 5. So this BFS way is actually really straightforward once you get the hang of it. This is usually the way you'll always use, especially in Java. So BFS is very straightforward, and it's a very easy problem to grasp, and there'll be a lot of other practice problems on Leetcode which have this type of problem.